continue from where we left last time, looking at the application of the different mass transfer we looked at one or two problems in last class, so we will look at more. So, one of the so last class we looked at one case where we had a lake system, and then we looked at what will happen to the, how do you apply that. So, we look at now something else. So, we look at a system that such as a river. Okay. So, in a river again the problem is, so in a stream, so normally we call this a stream. Stream is a flowing water, and we have say air and we have sediment. There. Three possibilities here. So, we are, in order to apply it in a box model, I think we have to divide this again into segments, and we discussed that. So, for the time being we will only look at one particular box, that we are not going to be predicting what will be the concentration downstream 1 kilometer away from the system and all that. So, that is not the in the scope of things, but we will see how that is also done. Okay. So, in this kind of system one very interesting thing is, so if you take a simple problem, one scenario could be, say there is a contaminated sediment, and I will come to this scenario a little later. So, let us say that there is a case where we start with the sediment. Let us say that there is a, again just as what we saw in the last class, we saw the case of what happens in land, there is a spill on the land, there can also be a spill on the sediment. So, this is a simplest case. So, let us say that there is a barge that is dropping chemical, and this chemical is what we call as a dense NAPL, DNAPL, or a dense non-aqueous phase liquid. The problem itself can be stated as spill of DNAPL. Dense NAPL is the chemical is, as the density of chemical is greater than the density of water. So, there are many chemicals, chlorinated chemicals, many of them have densities which are greater than that of water. So, they will, if you drop it into water, it will go down, it will sink very quickly, and it will settle down on the top of the sediment, and from there mass transfer will occur over a period of time. So, if there is a river that is flowing, so it is very easy for us, convenient for us to consider this section as a box, and mass transfer is happening into this section and then going into the next section and so on. But when it gets to the next section, there is a possibility that this will now get transferred back into the soil. So, we will look at that later, and that is a complicated process. So, over a period of time what happens that we will see in a minute. So, we will look at just this process as an example of extension of what we derived in the last class. So, spill of dense NAPL, and now we are interested in estimation of flux from sediment to water. Okay. So, this again like last class what we did, the flux will be K, this is K of A2 from 4 multiplied by rho A2 star minus rho A2 we will call it as rho A2. So, So this is rho A2, which is essentially coming from this previous section, rho A2. You can give it any name you want. You can give it rho A2 infinity, rho A2 previous one, whatever. So we will call it as rho A2 0, because this will result in a new rho A2 which is representative of this section. So this is rho A2, which is, this is rho A2 0. So so this rho A2 star is again, because this is pure phase. Now because we have written this down because it is this mass transfer in the water, this is in the water, this region, multiply in contact with 4, which is pure chemical. Okay. So therefore this will be the solubility of A in water. Just like what we considered in the last example where we spill something on land and it does not go into soil, it is staying as pure chemical. The rho A1 star in the last class we talked about, there is a vapor pressure of A. This is the equivalent of that in the solid. And then this mass transfer coefficient Ka24 is now the is a stream mass transfer coefficient. In the sense, this is not the same mass transfer coefficient as what you would see in an air water interface. This is not the same as, see, there is a Ka1, there is a Ka12 here, and this is Ka24 here. This is what we are talking about. We are talking about a pure chemical sitting here and we are talking about Ka24. This is different from this, it is not the same. So, and the correlations are very different because this system is different. It is a body of water that is moving over sediment. This is air which is going in whatever manner that is. Okay. So the problem now becomes selection of, then this is all it is, the equation is fairly well set. So the problem now becomes the selection of the mass transfer coefficient. So we will look at a set of mass transfer coefficients that we can look at, and there are many mass transfer coefficients. This a limited list of this given here. For example, we look at natural surface liquid phase mass transfer coefficients, and this list is there in your web page. So if you look at this correlation, it straight away says that it says that lake L by H is greater than 50, correlation for ethyl ether. So right here some information is already given. Length by H is, this is a lake which is a very shallow lake, which means the length is 50 times the width, the depth. So and it is made for ethyl ether. How do you know that it is only applicable for ethyl ether here? It is because in this correlation, this is a correlation Ka21, this is a water side correlation for evaporation into air. So from the correlation itself you can see that it is Ka21. So it is a water side correlation for in contact with air, water in contact with air. So it is at the air water interface, but the water side coefficient. N is for natural, do not worry about that is not relevant for you. It is taken from one of the books, but it says the correlation is just point, it is 0.094 Vx square. Okay. There is only one factor that is listed in this coefficient, in this correlation, it is velocity. It is a velocity, and this is a velocity of, air, not velocity of water, it is a velocity of air. Okay. It is a water side coefficient, but it is a velocity of air that is given. So it is wind driven turbulence correlation, and it is for shallow lakes. It is actually not very accurate because L by H can be anything. I can have H as 50 meters and L can be 2.5 kilometers. It is still a long, it is a deep lake. So it is a bit of a, it is not a good correlation in my opinion, but that is the best. If somebody gives you a correlation like this is the only thing you can use. So, two things directly you can see that there is nothing else in this correlation. There is no length parameter, there is no compound specific parameter, which means there is no diffusion coefficient, nothing. So, this is only applicable for whatever is the conditions they are given. For lakes, for this LH less than greater than 50, and it is for ethyl ether, and it is for the data is only valid if the velocity is between 5 to 16 meters per second. Okay. So, now what if you want to apply it for one of our problems. So, let us say if we want to look at the evaporation. So, we are going back to our old problem. So, we have water and air, and we have some concentration rho A2 equals something, okay, some value we have, we do not worry what it is right now, and we have some rho A1 infinity here. Okay. Now, we are worried about, we are looking at this concentration. So, we have Na equals capital Ka to 1 into rho A2 minus rho A2 star I will write it as this rho A1H. So, rho A1 infinity. Okay. Now, 1 over capital K to 1 equals 1 over small k to 1 plus 1 2, is that correct? So, these two numbers I need now. So, based on this correlation I look at this number. So, I have, so it is a lake. This is only for lake. If you are looking at a lake, Ka1 is 0.094 Vx square and K2, K1 is also given as 358 V8 AR. One of the things you have to also watch here is the units of this thing. Okay. This is all over the place. If you look at it, this is not normalized to SI units or anything. So, you have noticed that this is not a dimensionless correlation. This is a dimension, the correlation has dimensions, which means right hand side the correlation will be is Vx, and the left hand side the units will be whatever this is. This is not mass transfer coefficient that we have derived from our this thing. The dimensions are not consistent, which means that some dimensions are hidden in this coefficient 0.094. It includes some dimensional aspects, whatever for usually for Ka1, if we are writing the units for Ka1, it should be the flux is mass. So, for example, if you are looking at Na is Ma by L square T equals rho A2 is Ma by L cubed, which means K has to be L by T, yeah. But in that correlation it says Ka to 1 is 0.094 Vx square. The units of this is L square by T square. So, for this to be L by T, this has to be this constant has to be T by L. Well, weird. Okay. You can't analyze it like this. So, what they are essentially doing is they have measured mass transfer coefficient and plotted it against velocity of air, and this is the correlation they are getting, and that is all, that is it. So, that is a correlation, it is empirical correlation, and you have to follow whatever they are saying very strictly. You can't make your own assumptions and all that. This is what they have given. Okay. So, this is a correlation meant for ethyl ether and for the conditions of velocity, wind speed that they have given. So, it says 5 to 16 meters per second, and that is all. So, your velocity is below that, it may not apply. You have to take it with that bit of suspicion that it may not be accurate at all. So, in most of these cases we do the best we can, that is why it is called an estimate. So, let us say that our A is benzene, which has a molecular weight of 78. Yeah. This correlation, this Ka21, small Ka21 is a correlation for ethyl ether. This correlation Ka12, the next one for the air water, this one Ka12 is for evaporation of water. So, this correlation is for water. Again you see that same thing, it has a velocity term and an area term, but it has no no reference to any chemical there. So, you have to now, so this is only valid for water evaporation. This is an air side evaporation. This is similar to what we have been doing. We have said if you want to measure the individual coefficients, we use pure gas or water for either phases. So, they are using that, they are essentially doing that. So, water vapor evaporation. So, you have to convert both of these to benzene now. So, first off what we do is we pick a correlation, we pick those two correlations. If I am giving you an example, we are not asking you to use that correlation. But if you are looking at a system that is closest to your system, it says gas phase coefficient in lakes and or streams, this is only lakes. So, if your system is a lake and you want to look at this, we use these correlations as an example. Okay. Now, the first step is you use this, let us say we are using this correlation, we calculate the mass transfer coefficient for ethyl ether. So, we are using Ka21 equals 0.094 into V of x square. So, we know what Vx is, Vx is known. This again here if you want you can use this additional information that is given. It says Vx is measured 10 meters above the surface. Because in their experiment they have measured Vx as 10 meters above the surface. If your Vx is measured in a different height, you have to convert that to 10 meters height using one of those correlations we used for dispersion, using the boundary layer, those correlations, because this is only valid for that. Okay. So, this is the problems with correlation. So, you have to understand exactly, sometimes people do not give you full information, they will give you half information if they are not doing it correctly. So, if you generate a correlation, you have to give all the information with the correlation, so that people will decide whether they can use it for their system or not. Okay. This also assumes that there is no other process in the water that is moving the water. It says only wind induced correlation. This essentially assumes that, right. It assumes that only wind velocity is causing water side turbulence, and that is water sides changing. Yeah. So, we plug in all the values here into this and get the value for this thing. So, we get the value of K21, but it is for ethyl ether, and similarly we get the value for K12 which is 358 V8. So, 8 is again, wind is 8 meters above the water surface. It is all arbitrary everywhere, all around the place, right. Into area, and you notice that the mass transfer coefficients are all in centimeters per hour, the velocity is in meters per second in this equation, the velocity here is in miles per hour. So, I am just giving you an example of this is miles per hour, the area here is in acres. I do not even know what conversion for acres, you have to go and check what acres is. Okay. So, it is all over the place. So, you have to worry about these things. This is acres, and then again this is for water vapor only. Once you calculate this one, you have calculated it, you have calculated this, we have calculated Kb12 and Kb21, where B is ethyl ether here and B is water here. Now, you have to convert this to benzene, which is in your problem if you want to use these correlations. So, we use the scaling laws that we talked about, okay, and it is also given here, it is a suggestion that is given. Generally it is n equals to half should be used to convert to other volatile substances. So, this Ka1 is Kb1 multiplied by the molecular weight of A divided by molecular weight of B raised to half, sorry, this is 2. So, this number will change. So, sometimes people will give you a suggestion whether what to use there, 0.5, 0.6, 0.4 and all that, you have to look at that, and in an examination. So, I will give you other correlations which you can use to do this. So, which means that now we will take whatever value we get. So, ethyl ether, for example, for ethyl ether has molecular weight is what, CH2 C2H5 O C2H5, whatever the molecular weight that is, it is 48, 58 plus 16, 74, 44, yeah. So, it is not that big of a difference. Benzene is 78, this is 74, it will not be that different, it is the same, almost the same. But in the case of water, it will be very different. This is water molecular weight is H2O, molecular weight is 18. So, there will be a big difference between this and if you look at the correlation for Ka12 equals Ka21 to the molecular weight of A, sorry, yeah, B, by molecular weight of B. No, I think it is the other way around, sorry. You will have a decrease in the mass transfer coefficient. So, A is here and B, yeah, it will be decreased, it will be the molecular weight of B by molecular weight of A raised to half. So, for example, so molecular weight for benzene will be smaller than that for okay. So, you look at other correlations here, we have a few others and we can look at that. There is a correlation for water site mass transfer coefficient in streams. So, the one of the to avoid all that problems that we had in the previous two correlations, they are not good correlations, they are bad correlations for various reasons. One, it does not take into account compounds. So, every time I have to worry about what is this for ethyl ether, water and all that. So, the best correlation, a good correlation is something that takes into account all possible factors and it is a generalized correlation for a variety of scenarios for a particular geometry at least. So, for streams, if you are looking at water side coefficient for streams, the good correlations standard is where you have a dimensionless number. So, if you are here dimensional advantage is that irrespective of what units you are using, so long as you are using one set of units, you do not have to do any conversion business and all that. So, it is all there in one set. So, this is an example of a good dimensionless correlation. It is dimensionless to a large extent, but it also has things here. One of the things that you can look at it here is has this term called NSC. So, NSC is called as a Sherwood number, okay, Schmidt number, sorry, and NSH is here and the definitions are given there. So, this is Sherwood number, okay.